So in the previous lecture, we started to determine the properties of a semiconductor. To remind you, in a semiconductor, we have a conductance band, a valence band, and a gap. And as we said in the previous lecture, the gap is not so large, so there is a finite probability at room temperature or at the relevant temperature to get some of the electrons moving from the valence to the conduction band. And we wrote down this probability according to the usual statistical mechanics. The number of holes in the valence band, holes meaning the absence of electrons,
Didn't have it been 1 minus that one, the intensity?
yes, but pay attention to this change. That was the one line before it, and then we rewrote it in this way. Okay, let's start from where will we have mu, although we haven't yet calculated it.
In the conductance bands.
Second guess.
How do we find it?
No, where will it be? We didn't.
In the gap.
The answer is, of course, we have to calculate it, but educated guess.
In the gap.
In the gap. Why? Because, let's say, rule of thumb, mu is more or less the place where the population is half. Here it's mainly populated. Here it's mainly empty. So mu will pass somewhere in the gap. We will perform an exact calculation further on. But it's somewhere in the gap. Of course, its precise location will depend on mu. Right. So Let's start with very low temperatures. If the temperatures are already of order of the gap, basically the fact that I have a gap is cleared out. Because then I won't feel the gap so much. Okay, so I want to consider the case, small temperature. KBT is much or the vice versa, KBT so KBT could be considered a perturbation upon the differences in energy. Under these conditions, if E minus mu is much larger than KBT, so do I really need this plus 1 here? No. So I can take
Can you approximate it by the step function?
no, it can't be approximated by the step function because if I put in here a step function, I get there's no particles at all in the conduction band.
And that's
So that's throwing the baby with the bathwater. You leave nothing. What you leave here is actually that you have here a small exponential tail. So something nevertheless happens. If it's really huge, so all I have to say is there's nothing there. Okay. Yeah.
Shouldn't it be without a minus because you already did mu minus epsilon?
U minus epsilon, but in this case,
So it gets the same thing then. You did minus times minus u minus epsilon.
mu minus epsilon is larger than KBT.
Yeah, so we just dropped the one.
So I just drop the
Yeah,
one.
no, but look what you wrote. We moved minus outside of the parentheses of the mu minus epsilon.
Yeah, but that's the minus 1.
Oh, okay. Yeah, I see.
Just 1 over e to the power of something is like e to the minus power. Okay, let me define something that will help me in the calculation. At the moment, I didn't do really nothing. I only shifted something of the definition into n, large N and large P, and put out a constant. Pay attention, this is a constant. This is not the E that appears in the integration.
It's the E that appears out of the what we defined as the domain.
Right. So let me rewrite the actually define NCT and PVs.
Excellency.
Yep. Let me finish writing it down and then we'll check. Okay, what did I do here? Well, if I'm allowed to write it in this way, I can write it as a multiplication of something till mu and from mu. So the part that depends on mu, I moved outside. And that's all I did, nothing more. Why is it useful? Because it lets me give this function, these functions, without calculating mu. That you remember calculating mu is always difficult. Okay, so let me do the calculation. I have to know something specifically on V and C, on the density of states for valence and conduction band. What do I know? Okay, all that we did in the last lecture was telling you, look, you can approximate it as you wish, nearly free electrons, tight binding, writing it down as discretization of space. All of it is good and nice, but what do we know on the behavior close to EC or close to EV? Free electrons up to a correction in the mass. Okay, that's all I need to know here. So, details go into the mass, and as long as it falls off exponentially when I move from EC or move from EV, details are not very important. Everything goes into one parameter, the effective mass. Well, basically it behaves like square root of E from the point of EC or EV. I have here an absolute value because for one of them I'm going up, for the other one I'm going down. Power of half, if you remember, for any three-dimensional case, the density of states behaves like e to the power of half. And constants, go back to that calculation for free energies and see the constant, and the only place that I take into account the details of the band is I write that m, the effective mass for the conduction or valence band, which could be different. It depends on the lattice structure, but I don't care. Okay. So I can do this is an easy calculation. Why? Because it's just the power half times an exponent, something I can do. And I end up with NC and PV as function of t. Okay, so this is really just a function of t, and the band properties come into the masses. That's all.
Things like the thermal wavelength, right?
Yeah, it's actually the thermal. Okay, I have here, as long as I didn't put in impurities, and I haven't yet put in impurities, I have a very cute connection here. Let's multiply NC by PV. Am I allowed? Yeah, why not? Okay, so NC and PV times exponentials. Wait, I lost mu. Right. So the number of electrons and holes, if I multiply them one by the other, just depends on the gap. That's all. Can say temperature, of course, gap divided by the, that's the main influence. I have still a small influence of temperature here, but as the gap becomes larger, the number of holes and electrons, either in the conduction or in the valence bands, drops off exponentially.
These are densities, right?
These are densities. Okay, if I have no impurities and I don't inject charge from outside, what do I know?
The number of holes is the number of electrons.
Exactly. The only way that I can get a hole is the fact that it was created by moving this electron to the conduction band. So I actually know that NC is equal to NV, which for some reason got the notation of NI. Intrinsic. It's the number of electrons that come from within the system and not from the impurities. Although, if you ask me, this is confusing because as well as intrinsic, it could stand for impurities. Should have chosen a different notation. So, Ni
NV is PV or
PV, sorry.
comes from the fact that the charge is neutral, right?
Right. No, well, a bit more of it. Charge is neutral even when I stick in impurities. Because what is an impurity? The easiest way to think about it is an impurity with a different, is an atom with a different number of electrons in its external shell, or however you want to define it. So materials are always, and I'll give you a caveat about it, materials are always neutral except if you gate them. Everyone knows here what I mean by gated. There are two ways to change the population for a semiconductor. One is I put in temperature, I put in impurities. So I can change the number of electrons in the A different way is take a huge metallic plate, and that's a gate, and put an electric potential. Then part of the charge will move to the other plate like in a capacitor. That's gating. Used ubiquitously in semiconductor technology, but then the material by itself is not neutral. The material plus the plate is. And anyone who does anything with semiconductors knows that you can do very interesting stuff by putting a gate on a system.
Isn't the power here is 3 over 2, not 1 over 2?
Very good. 3 halves here. Just by comparison from here to here. You know, good that you noticed. Okay, so let's write it down explicitly here. Okay. Now we're in actually a good position to calculate mu. How can we calculate mu? Very simple. We will compare NC to PV. They have to be equal.
Like approaching to a phase transition.
I don't really need here the concept of phase transition. It's simple Boltzmann occupation. What do I gain by introducing the concept of phase transition here?
Anyway, the phase transition is when it comes out of it's not equilibrium, like when it tries to tend to equilibrium.
Oh, I don't want. Phase transitions are extremely interesting and requires their own discussion.
This isn't statistical mechanics.
This is a simple Boltzmann occupation. We solved even, we threw out the quantum concept here by getting rid of 1. We have now only exponential terms here. Well, we have mu and it's determined. Okay, how do I get mu out of this game? Well, note that everything except for mu I know. So let's apply lam on both left and right hand side. Okay, let's see what it tells us. First, this is just algebra. Fancy name for moving between the left hand and right hand parts of this equation. If t is equal 0, mu sits exactly in the middle of the gap, as we expected. If mv is equal mc, the two bands have the same density. It always remains there. What? Makes sense. Because if it's the same density, if I pull out an electron from the valence and put it at the conduction, it's the same density, so I keep the same distance. Therefore, it doesn't move as function of temperature. If the densities are different, let's say there's more density in the conductance than in the valence, then I'm pushing the electrons that I'm pulling out from the valence into somewhat lower states in the conduction. And then I'll have some linear correction with temperature to the position of mu. Okay. So we solved the case for the semiconductor with no impurities. Okay, just before we go into what is an impurity and what is the game that it plays, let's just assume that we have a situation where the number of that I have an additional electrons or holes injected into the system. How? Let's say by a gate. I don't care at the moment. So what happens? This is broken, right? Because I told you that I injected either holes or electrons into the system. So in this case, let's just define the excess number of electrons in the system as delta N. Actually, to keep it simple, delta N. What is the difference in what we had before? I'm keeping this definition, right? Here I didn't have any assumption about about if I have excess electrons or holes. Didn't assume anything. I just put in the temperature and looked on the population. Where is the population important?
Just in the deviation between them.
Right?
The borders.
In this assumption, which I don't assume anymore, which will lead to a different determination of mu. But that shouldn't surprise us. It's always in the definition of mu that the population comes into a statistical description of the number of particles in a system. Nowhere else.
So it's kind of defining some sort, that's defining equilibrium, and now we are doing...
Well, this is defining some connection between NC and PV, because even if I have to begin with some asymmetry between the number of electrons and the number of holes, when I switch on temperature, still any additional electron will come at the expense of additional hole. The only point is that I don't start with this assumption that I started at temperature equals 0, no electrons in the conduction, no holes in the valence. Here I say, well, even at t equals 0, I can have either additional electron or additional holes in the game. What I can still do is create electrons or holes out of the temperature, because anytime I switch on temperature, it will end up with electrons moving to the conduction, creating holes. This has to continue. So the only place that will come into account is the definition of mu. So basically, didn't switch them. No, I switched them. Oh, I didn't switch them, I just put a minus here. So this just states what I said. The calibration of the number of electrons and holes depends only on the new mu I compared to the old mu. Okay. So, what is an impurity? Let's say I have a lattice, silicon lattice, a germanium lattice, whatever lattice. Well, if it's a true lattice, all the atoms are silicon or germanium, whatever. They appear, of course, in the appropriate lattice structures of these materials, which tend to be diamond. I can't show you on the blackboard a diamond, so I'll just plot it as a simple cubic. Okay, so let's assume
Supposed to be close to an FCC, isn't it? Diamond structure?
a diamond is an FCC which has a brevet, which is another FCC at some offset. But I can't plot you even an FCC, so certainly I can't plot you a diamond here. Okay, so this is a pure, let's say, germanium lattice. Okay? Germanium, silicon, carbon all have 4 valence electrons, and they have, all of them are well connected to the other germanium in chemical bonds, and all are happy, or as happy as they can be. They have covalent bonds with all other atoms, everything is good. Let's assume that for some reason one of the germaniums is replaced by arsenide atom. Arsenide, for example, has 1 additional electron in its outer shell, 5 instead of 4. Okay, so chemically speaking, it can put in 4 of its electrons in the same chemical structure with the same covalent bonds as if it was a germanium atom. Okay, 4 are happy. Stacked with an additional electron. Now, you can say, okay, so this atom, sorry, this electron is free. Yeah, it can be everywhere. Not exactly. Why? Because if this guy goes too far from the arsenide atom, it will leave here 1 additional charge, positive charge. So it can't just wander around as a free electron. So it's bound to the impurity. Okay. Then you can tell me, okay, it's very similar to a hydrogen atom. Right? Forget everything that happens for the all other electrons. They are satisfied. The inner core doesn't care about what's happening outside. 4 of the electrons in the valence are chemically satisfied with their covalent bonds with the other atoms in this game. And this guy sees a 1 positive charge. Therefore, we have a hydrogen atom.
But in terms in the transport in the lattice, we should expect some sort of scattering of a Coulomb potential, right? So that it's not the same.
Well, you are right that I forgot some small detail, which is the fact that, okay, I have a positive remnant here and a negative electron here. And if I would have been in vacuum, that would be exactly the description. But I have here a whole sea of additional positive and negative charges in this game. So what can these guys do, the additional electrons and positive charges going around there? Okay, to give a real detailed description of this, of their effect, is difficult. But already for 150 years at least, we were able to give some description of what's happening there. That's not exact, but captures quite well the behavior of all this complicated structure of atoms and electrons and whatever. Let's say if you have a Coulomb charge, the usual in vacuum, what do? You write down the Coulomb potential
What do you want? Its equation of motion?
Right? That's what you have written in high school.
But which problem are we trying to solve?
The same problem, but if I would tell you in high school, this charge is not in the vacuum, it's in a material, what would you have done?
Not.
No, epsilon naught is the vacuum.
Yeah, it
Right.
can change.
It will change to epsilon. Right? And therefore, all that is happening is that I take all the complicated behavior of the charges in this material and say, look, you can take it into account by correcting this simple parameter.
It's just a guess, or how? Why is it okay?
Why is it okay? Well, if you're in Maxwell in 1860, I checked it experimentally, and that's what I get. Okay, if you're nowadays, you do a complicated calculation and get to the point where you basically say, well, it's good enough.
You start with the answer, you approximate until you get there.
More or less. It's a very complicated system. I'll discuss in a moment this guy. What is important about this? Epsilon is always larger than epsilon 0. That's the important thing to remember. In most semiconductors, it's about 10 times larger. So what does it mean? It means that the Coulomb interaction is partially screened by all these electrons around us. Makes sense? So, and that is the final physical description of this impurity. We have an hydrogen atom, but with a much larger Bohr radius. Or if you want, a much smaller energy scale. And that is actually the best description that we can at this stage give for an impurity in a semiconductor. Okay, I want... You think that everything is good with a vacuum? No. Why? Because if we're going back to Dirac equation, you can create electron holes also in the vacuum. So you have screening of the vacuum by additional charge. And that creates a small but measurable shift in the states, in the energies of hydrogen atoms. That's known as line shift. Was measured in 1947, started the race towards a good description of QED, quantum electrodynamics.
But isn't violating the conservation of energy, because we did a calculation that you cannot do from in the vacuum create a pair of positron and electron in the vacuum.
Okay, you want I'll give you the hand-waving explanation, although it's not the full picture, but this is not the course for it. In the course of QED, come and ask this question. Conservation of energy is correct only on long times. You have uncertainty relations between energy and time, and these electron-hole pairs can pop up from the vacuum for short times, and even that it pops up for short times, it has corrections.
As virtual particles.
Right. So, I'm sorry, probably nothing went through from this explanation. You have interaction with virtual particles. In order really to do it, you have to put in two ingredients that you don't have yet. A good description of an electron, not Schrödinger equation, but Dirac equation, and a good description of photons, a field theory. Both of them you don't have. When I'm writing this thing, the photons are not quantum field theory. But it's beyond. The only point that I wanted to say is, here you don't have virtual particles. You have real electrons swimming all around you. They can create they change their position a bit by this additional electron. They screen this electron, and therefore the interaction that it feels with the positive charge is different. How is it different? Well, I don't know to do the calculation, but I know empirically that you replace E0 by E and you're happy. That's all I need here. So. So to remind you, the Bohr radius two things are different within this material. First, your charge has not the same influence as what's happening usually. You replace 0. Let's just for consistent write it as E times 0. And what else is not correct?
The mass.
The mass is not correct. So the mass is exchanged for the effective mass that is relevant within this lattice structure. So if I write down R0, the radius of this strange hydrogen atom So if I plug in typical numbers, let's say for germanium here, so it's 100 times larger radius than the Bohr radius, so it's of order of something like 50 angstroms, not half an angstrom. And the energy, let's say the ionization energy, to be mixed up with the epsilon. So you remember, or hopefully you remember that the ionization energy for a hydrogen atom is about 13.6 electron volt. Of order of 0.1 electron. So, what is happening here? So, this guy, which, if it would have been an additional electron just going into the conductance band, would have parked itself in the first open state in the conductance band, basically says, sorry, I'm tied to my to the positive charge in the impurity atom, and in order to ionize it, I need another 0.1 electron volt. So what does it say?
It's way cheaper than it would be at the vacuum.
Yeah.
Because of the...
It's a factor of 1,000 cheaper. Because generally speaking, in most semiconductors, M is about 1/10. M star, the effective mass is an order of magnitude smaller than M, and the permittability is one order larger. So here we had a factor of 10 to the square, and here we had 10 to the minus 3. So what does it mean? I have here EC, EV. Okay, I put in an impurity. This impurity has an additional electron. I'll call it a donor for obvious reason. It has an additional electron to donate to the system. This impurity exists somewhere in the system. Okay, so I have some state about a 0.1 electron volt lower system, and I have an electron tied to it. So this is, of course, usually I have a bit more than one donor. So I'll have one here and one here and one here and one here, and I assume that they don't interact. It's still a low percentage of donors. For typical semiconductors, 10 to the minus 5, 10 to the minus 6 of the number of atoms are replaced by donor atoms. So they exist everywhere, and I have a donor band a bit below the conduction. I could go and tell you the same story for an atom which has just 3 electrons in the valence band. Then it's missing an electron. We'll try to steal something from the conduction band. So here I have, from the valence band. What does it matter? I changed the scale of behavior of the system. Why? To kick these donors into the conduction band is much easier than bringing them from the valence band. Why? Because the difference is much smaller. Let's write down numbers. Okay, so for silicon, the gap and for germanium.
Does the crystal structure change with the acceptors?
Yes and no.
Because you don't have enough electron to create the bonds.
So the answer is, as long as the concentration of impurities is of the orders that I speak about, 10 to the minus 5, 10 to the minus 6, the structure almost doesn't change.
You have one less bond.
I have one less bond that I think about it as a bonded electron at some large distance. If I have an additional well, they can scatter particles, electrons ago. It has influence on the conduction. But between me and you have other defects in these lattices that also scatter. So putting in a small number of impurities, the main difference is in the population, not in the global properties of conductance and things like that. Okay, 0.67 electron volts. So, rule of thumb, typical semiconductors gaps are of the order of 1 electron volt. Carbon, for diamond, it's higher, 5.5 electron volt. So I'll call this EA, energy of the acceptor, ED, energy of the donor. So aluminium is a typical impurity that has 3 electrons, therefore it's an acceptor. and we get, they sit a bit above the valence energy, but only a bit, of order of 0.1, 0.01 even, depending on the material, electron volt. So they are much closer than EG. Yeah. So, what is KBT?
Energy of the system.
At room temperature. Give me an order in electron volts.
0.86,
Around a quarter of electron volt. You may be more exact than me, but I remember a quarter of an electron volt. Look at these numbers. Meaning in room temperature, these donors are actually in the conductance band. These acceptors take electrons out of the valence bond and create holes. So basically, just putting in a small number of donors or acceptors completely changes the properties of the system. Because the numbers that I get from here, if I have a high donor concentration, is much higher than what I would have received from jumping from the valence to the conductance. Okay, so basically all technology that you know are based on this fact. What do I mean? Okay, we'll see how diodes are built. We'll see how transistors are built. Or at least get some illustration on how they are built. But let's look, at the moment, we can look on the simplest device that I can build on silicon. What is that?
Integrated circuit?
An integrated circuit. That's actually the concept that really turbocharged the electronic industry. All of you have heard, or I hope that all of you have heard, about solid-state transistors and how it revolutionized everything. Yes and no. Yes, in the meaning that the fact that you could put a solid-state transistor of size of, at the beginning, 1/4 of a millimeter, 1/2 millimeter, instead of tubes that took you a couple of centimeters, burnt out easily, and you had to replace it every few weeks. Yes, certainly, it was a change. But how many transistors do you have in any device that you're using nowadays?
Billions.
Billions. Now, if you simply have to take these transistors and connect them. Well, you're building circuits, right? You have to put copper wires or gold wires or whatever wires you're using between them. There are things that once you are getting to devices of a few tens of transistors, life becomes complicated. Just connect all this stuff together. What was the first solution to it? Before they integrated.
Etching?
No. Well, the first solution was the printed circuit. Right? Instead of just connecting by wires, you print wires on pieces of insulator, plastic or whatever, and then you have some connections that you stick your transistors out of it. If you open old electronic devices, you'll see these printed cards that you have capacitors, transistors, whatever attached to them. So that makes life a bit better, but still you can't get a lot of transistors in this thing. So what was the great idea behind integrated circuits? Okay, don't do only the transistors or diodes or capacitors on a semiconductor device. I also create the wiring on the silicon device. And how do I do it?
Lithography.
Lithography, but what is lithography?
Chemical etching of the material on the semiconductor.
Well, it's a bit more of it. Okay, let's say you want to create a transistor here, want to create a transistor or diode or whatever here, and you want to connect them by a wire. A wire is some device that carries current. Doesn't do anything clever, just actually, copper or gold wire would be good enough, but as I said, you can't put a lot of them. Okay, so how do you do it?
You do by this line.
Exactly. You spatially put these acceptors or donors only along this line. You don't put it anywhere else. Okay, these additional electrons, which move to the can't go very far from here. So this area will be metallic because it has electrons in the conduction band. This area won't be metallic because the conductance band is almost empty. Okay, so how do you put impurities only in this region? 2 steps. First step, you have to create a very clean silicon or germanium lattice. Because if it's not clean, you'll have impurities everywhere. You don't control it. Your current will go everywhere. So that's the first step. And till today, one of the hardest steps. These fabrication facilities of Intel or whoever is doing nowadays,
NVIDIA.
No, NVIDIA doesn't create. It doesn't
Okay, silicon.
doesn't do anything. in the meaning of manufacturing. They gave this HTSC, what's the name of the Taiwanese?
It's one of those fabs.
Yes, I think NVIDIA is almost Samsung, HTC, and a few remaining Intel. TSMC. Most of the manufacturing is done there. Those guys know to create lattices of diameter of a few meters that are completely clean. No structural damage, no impurities, and that's to get to this stage, $10 billion for each fab. It has to be very clean rooms, processes, everything around it. Okay, so you did this. How do you get the impurities into the lattice? Basically, you say that well, you don't say, you do. You build upon the fact that if you put a gas of some kind of atoms close to the surface, some of them will diffuse inside the lattice. So you expose your silicon wafer to some
Vapor deposition.
Vapor deposition. So that's the way the impurities come. Now, how do you control the fact that you'll have only vapor deposition in some region?
You etch everything else off.
Or,
You cover it.
no, you cover it. You cover it with some mask, which is usually some kind of polymer or stuff. Then comes lithography, which is a point of removing this mask only from a certain region. Then you expose it, and then you get this area which is doped, and this is your metallic wire in the system. And nowadays you do it 10, 12 different layers at depth. You also do the transistors themselves, but it's all integrated. It's all at the end of the day, putting in impurities into a silicon or germanium lattice at the points that you want them to go in. So controlling it so it's nowadays 3 nanometers thick. You can't well, in the good old days, you could use light to create, to remove the mask because a few thousand nanos were good enough. Then they moved to all kinds of games to get lithography on smaller and smaller scales. Yeah.
But now you cannot go more than nano, right? Because there's the
Well, you have all kinds of problems. It's a huge. That's why only very few fabs move even to nanos. Well, think about it. You deposit by diffusion. How do you want to have 2 lines, but no electricity going from one to the other. You don't want that if this transistor speaks with this transistor, it will also start something in some signal in another transistor. So you don't want impurities diffusing. How do you stop it from diffusing in a very... Well, you're working at room temperature. Actually, I'll give you, you're working at much higher temperatures than room temperature because put a hand on your laptop, it's hot. How do you stop some kind of charge that will accumulate there because of temperature? how do you stop tunneling between these things? All of them are a problem, which probably some scale of around a nano will be the hard limit of pushing this technology. Okay, but pushing it to 1 nano was a Herculean effort during 50 or 60 years to get there. Okay, so what we will like to do in the next lecture is basically, in order to create either a wire, or a simple electric device, it's enough to have a homogeneous doping of either acceptors and donors. In order to create something that does interesting behavior, like a diode, you have to have different doping at different regions and bringing them together. That's what we'll do in the next week. Okay, I want to say that from the assignment the last lecture, at the end of the day, 2 people came up with it. One of them already submitted very nicely. And I'll give another assignment next week, but you'll have to be either here or online and get it at this point. So.
So you prefer type binding because once you get to more complicated structures like non-simple cubic, it's easier to graph it. Right. So you don't have to write several lines of code. You just do the function, and it gives you the diagram perfectly.
Right.
You don't even have to do try to do the halfway from the nearest neighbor, perpendicular.
No, you don't need the.
Yeah, like conceptually, NFE is easier. Mathematically, type binding is
Right. Well, I'm working on models on the computers and always using type. I don't even think about it.
It's more accurate, and you don't have to do as much math.
Right.
Well, it says like, wow, type binding. I then used type binding to make sure it was correct the answer I got even. I was like, am I supposed to, that was